Okay, so I'm very pleased to talk to you this morning about some work we've been doing on the Event Horizon Telescope. And I guess this talk's going to be a little different than others. I'm not going to focus particularly on one method or one technique for data analysis. I'd like to kind of weave a broader theme. But the general idea is that we're trying to make pictures of black holes, and we'd like to understand how astrostatistics can help us do that. And before I start, let me just say this is work done with a lot of people, many here: Andrew Shale, Ramesh Narayan, Lindy, Katie Bowman at MIT, and many others. So it's a big group. Okay, so most of the talks so far have really focused on astrostatistics as the application of statistical methods to enhance data analysis. And I guess I'd like to think of astrostatistics as much broader than that. I think that statistical methods can help us to both develop better mathematical models for analyzing sources, and also to understand the astrophysics of sources themselves better. And this is basically because we have these phenomenally complex systems that we're studying, and that complexity often leads to statistical universality. So I'd like to just give a few examples where I think that this universality can enhance our physical understanding. So for starters, interferometry and polarization. Now, these are two fields that I think for people who don't work on them are sort of black boxes. They're very difficult to understand, and interferometry in particular, people think of it just sort of as magic. It just produces this incredible resolution. And I think statistics can really clarify how interferometry works for those who aren't specialists. So in the most general formulation, what you're looking at is some astrophysical source that's emitting spatially incoherent Gaussian noise. And so this assumption actually works well for all known astrophysical sources, including pulsars and masers. So it's a very simple statistical framework for the source. Now what that means is that far away from the source, you're observing some Gaussian random field. Okay, and a Gaussian random field under fairly weak regularity assumptions is completely characterized by its covariance matrix. So the game in interferometry is just to estimate this covariance matrix. That's it. And so every pair of telescopes estimates one element of this spatial covariance. And we call this a visibility in interferometry. But that's the entire problem of interferometry. Now, it's slightly more complicated. Each telescope typically records two polarizations. And in interferometry, we usually use right and left circular polarizations. So for every pair of telescopes, you actually can estimate 4 covariances. You can estimate right, left, right, or left. Okay, and it's no accident that there are 4 of these. This is called the coherency matrix. There are also 4 Stokes parameters, which maybe you know. These are what carry all the polarization information in more typical applications. And it's kind of interesting that Stokes parameters, they have their role because they're things that you can directly measure in optical. Whereas for us, our direct observable is the coherency matrix. So you might wonder, how do you go back and forth between these? Actually, all you have to do is project the coherency matrix along the 4 Pauli matrices, and that gives you the 4 Stokes parameters. So all of this from interferometry to polarization, when you think of it from the perspective of statistics, becomes very simple. And you don't have to worry about the details of your instrument very much if you just want an abstract understanding of it. So the Event Horizon Telescope is this effort to equip existing sites with the necessary instrumentation to do millimeter VLBI. So this is all the sites that we'd like to add. And the key here is that when we're done, we're going to have an angular resolution of something like 20 microarc seconds, which is comparable to the size of the event horizon of our galactic center supermassive black hole. So we want to make pictures of a black hole. So tying this to what we've already done, first, this is a sample image of a black hole from Avery Broderick. And what you see here is that it's bright on one side and faint on the other. That's because there's this accretion disk around the black hole, and it's boosted when it's moving towards you and deboosted when it's moving away. The black hole is sitting in the middle, kind of casting a shadow on that emission and so forth. And that ellipse at the bottom is telling you about the angular resolution that the EHT will have. So you see that once it's finished, we'll be able to see these fine scale features of the black hole. Now, as I said, what we're after is this covariance matrix connecting all of our sites. And so again, it's this kind of remarkable thing that in a VLBI campaign, you have to record the full coherent field at every site. And at the end of all this, it takes up a petabyte or so of data per observing run. Then what you do is you ship it off to a supercomputer, and that just calculates all these covariance elements. And so once you're done calculating those, your data set is reduced to kilobytes or megabytes. And so again, the key is to break the data down into their statistical essence and to understand exactly what it is that we have to work with. But that's partially responsible for the rapid growth of radio astronomy recently, that it's really a problem of computing. Okay, another example of this where I think statistics can really help reduce astrophysical complexity is with pulsars and scattering. So for radio waves, when they propagate through the interstellar medium, they're scattered by density inhomogeneities. And this is a very generic result. And so you have this turbulent interstellar plasma, and that's acting like an irregular lens through which we have to study these sources. So you have some pulsar, it's emitting noise, and pulsars are particularly complicated. Each pulse from a pulsar looks different. People who don't work on these sometimes don't realize this because all you ever see are average profiles, which are very steady. But actually, every single pulse is like a fingerprint. And so they're changing quickly. You have this random scattering, and then you have your instrument, which is adding background noise and so forth. So it's a very, very complex problem. And we'd like to understand this in the simplest way possible. So to get to universal statistics, we analyze the data in kind of a funny way. We form dynamic spectra of the pulsar, but we form a single spectra every time the pulsar turns on. So normally you'd want to resolve as the pulse is turning on and off and see its shape and so forth. Here we're just going to form one big spectrum with all of that information. And so the pulse is changing, and that's going to mess up your spectrum. But we're doing this to get at the statistical universality of the signal. So once you do this, you can look at the statistics of the amplitude that you see. Okay? And the statistical form, the probability distribution of these amplitudes have a very interesting shape. You'll notice there's an extremely high tail. So in this particular example for the Vela pulsar, you see occasional samples that are 50 times the mean. This is something you would never see for Gaussian statistics. And this is a very special interaction between the noise of the pulsar itself and the scattering. But what I want to point out here is that each of these models, these green models on top of the data, don't require any fitted parameters at all. It's completely universal. And so this is very powerful. It allows us to study physical properties of the source without making detailed model assumptions about what it might be doing. So the departures are where all the information have to be. The departures from those green models, the residuals of them, have to be what contains physical information about the source. But it's when analyzed in this particular way, these departures are also universal. They can be described by a single parameter. Okay, and so here, what we're looking at is pairs of pulses that are then averaged together. And so as you look at the statistics of those, these residuals can be described by a single parameter at each lag of averaging. And that depends on two things. One is that the scintillation pattern is becoming decorrelated between those two instances of averaging. The scattering is evolving. The other is that the pulsar has a finite size. And so this is the same reason that stars twinkle, but planets don't. An extended source acts to quench the scintillation. It'll damp out some of that variability. And we can study that very generically in this particular way. And using this, we can estimate the size of the emission region of the pulsar, which here is about 4 kilometers. The pulsar is sitting 1,000 light years away, so this is an angular size of about 100 picoarcseconds, or about the angular size of a virus on the moon. But we can do this, again, we've reduced the problem to a way where the statistics are universal, and that's a very powerful tool. We've also been thinking about how we can use these types of techniques to analyze the refractive scattering of AGN. So for a long time, it's been realized that scattering causes the appearance of an AGN to be broadened on the sky, to be kind of blurred out. But it turns out that this is only true if you average over an infinite amount of time. If you look at it just one day or, for one observing epoch, what actually happens is that the AGN looks more like, this image behind the engines of a jet. There's all sorts of small-scale power, small-scale substructure introduced by the scattering. Now, the complicated thing is that this blurring effect of scattering gets weaker as you go to high frequencies. This is why the EHT is going to high frequencies to study Sagittarius star, whereas the substructure effect actually gets stronger at high frequencies. And so this is something we really need to understand for the Event Horizon Telescope. So one thing that we've done is we've developed simulations to show what the scattering would do to various images of AGN. And as you can see in this image, it'll cause a lot of different effects. It causes slight distortions of your image. So if you want to study a ring from a black hole, and if you think distortions are signatures of departures from canonical GR, we need to understand whether those can be confused with effects from scattering. They also cause flux modulation. So their different patches of the image become magnified and demagnified. So over time, you get rapid variability of the total flux of the source. And one recent interesting example of this is that there was this fast radio burst reported where it had an afterglow associated with it, this rapidly fading afterglow. And one thing that was very interesting is, well, with an afterglow, you can get a redshift for the source, and that's why it's so special. You can then estimate the density of the IGM. But this paper by Peter Williamson and Ido Berger have now very convincingly shown that rapid variability wasn't an afterglow at all. It was just this scintillation, this exact effect of the AGN. So this type of effect is not just important for the EHT, it affects a lot of different observations. So for Sagittarius star, we have to worry about this type of effect introducing new things. So on very long baselines have the highest angular resolution. And so it turns out that these are particularly susceptible to all this small scale stuff. So for Sagittarius star, if you go to long baselines, you're not seeing the source in exquisite detail. You're just seeing all this small scale power from the scattering. The thing that we'd really like to understand is how this affects closure phases though. Okay, so closure phases are this kind of hybrid phase. It's a good VLBI observable, but it's very difficult to work with analytically. But anyone who works on VLBI will tell you that all the information that you need if you want to form images of a source, it's all in the closure phases. So we want to understand how this scattering causes jitter of the closure phases. The problem is that, first of all, phase is not an analytic function. It's not even continuous. It can jump by 180 degrees abruptly. So it's very difficult to work with in general. To estimate the fluctuations for this particular data set, what we did is we generated lots of simulations. But because the effects of scattering are changed depending on what the intrinsic source is. So this doesn't actually give us any power to investigate, say, a class of sources, and it's very computationally expensive. So we'd really like analytic methods to estimate the closure phase, but it's this very messy, observable, and it's hard to work with. So the question is, can we use any sort of tricks with universality of statistics to get at this? So just as one example, here's one approximation for the closure phases when we make the assumption that the closure phase fluctuations are small. Okay, the only point of putting this equation up is to say, look, it's a big equation, it's scary. Each of these functions is also complicated, and the point is that this is not tractable, it doesn't teach us anything, it's not interesting. It at best solves our problem in a few special cases. What we can do though is we can use the same trick as in interferometry. We can get an exact form just by saying the statistics of these fluctuations are Gaussian, so they have to be described by their covariance matrix. So once we estimate that, we can generate Gaussian random samples with the same properties, and we can quickly estimate the closure phase on any observable, or the closure phase for any source and any observation. We could actually estimate more complicated quantities as well. So this is just comparing that approximate form with an exact method using this Monte Carlo technique. And you can see that they agree in the small noise regime where the approximate form should hold. But the exact form is actually simpler and it holds everywhere. It doesn't come out of any analytical treatment. You have to realize the statistical universality of the problem to be able to identify that you can use this sort of trick. Okay, so the next question is, how do we actually mitigate the scattering for the Event Horizon Telescope? How do we deal with all this small-scale power? And what we've arrived at is that we need to be thinking about imaging in a new way. We can't think about imaging the way that people always have for VLBI. So we're starting to think about a new technique called Stochastic Optics. And this will be a general framework that's kind of analogous to adaptive optics for optical observatories, where you're trying to mitigate the effects of scattering in the atmosphere. And so the idea is, instead of just making an image of your source, you're going to make an image of your source and the scattering at the same time. And in this case, if we did have this particular image and particular scattering screen, as you slide the screen across onto the image, it introduces all this small scale power. But we're going to use just one data set to try to estimate both of these. That might sound impossible, but I think that some analogies with adaptive optics make this promising. So firstly, adaptive optics has to act on timescales of something like 10 milliseconds, whereas for us, the scattering is essentially constant over a night. So we only have to solve for one screen per observation. The next is that in adaptive optics, the scattering in the atmosphere is achromatic. So if you have observations at two frequencies, it doesn't actually help you at all. Whereas for the EHT, it's actually steeply chromatic. And so if we have observations at two frequencies, we can use one to solve for the scattering, where the scattering is strong. Then we can apply that to a case where the scattering is weaker to improve the imaging. The next is that in adaptive optics, you don't record any phase information. It's all done in real time. Whereas for the EHT and for VLBI in general, you're recording the full coherent signal. All of this analysis can be done in post-processing. And then, of course, adaptive optics, they have lasers and guide stars and all sorts of stuff to help them. We don't have any of that, but we do know the power spectrum of the turbulence. And that turns out to be extremely constraining. So just some very preliminary examples on this. Here's an example image. This is actually the same image as earlier. And this is what it would look like before any interstellar scattering at all. This image is showing how it looks after you do that time-averaged blurring effect of scattering. This is the effect that was always studied. The third image is what we would actually see in one night of observation. All this small-scale structure is superimposed on top of that. And the last panel is just showing you the phase screen that would cause this. And so what we want to do is we want to understand how observations of this image would allow us to make reconstructions of the first one. Now down below I've shown you how typical image reconstructions would work on this. What happens is that when you try to de-blur the effects of scattering on this, you end up concentrating all your flux in small patches. So if you reconstructed this, you'd say, aha, I see two lobes in a jet, I see outflow, I see all sorts of stuff, and you'd be completely wrong. So we have to understand how to gracefully integrate the limitations of scattering so that we don't get images like that and deceive ourselves. So this is what we get when we try reconstruction with stochastic optics. So here, what we've done is we've reconstructed this phase screen at the same time as the unscattered image. And those together are making an image that would be sort of predictive of the single epoch image that you would see. And you can see that this no longer has those sharp, spurious features. But more interestingly, it's actually reconstructing the phase screen pretty well. This is with a simulated observation with thermal noise and everything else. So it's looking very promising that we can actually account for the scattering using a statistical framework. And the nice thing about this is once you have the scattering screen at one frequency, you have it at all frequencies. And you also have it at all polarizations. So we can wrap this into a more complex framework. We're using multiple frequencies, full polarization, and so forth to improve imaging fidelity with EHT. But the one thing that I want to add about this is that VLBI imaging in general is sort of a maximum likelihood approach to a problem. We're trying to find one answer given all of our data and to interpret that in one particular way. It's very rare that anyone tries to analyze, uncertainties on an image or even define what that might mean. And so what we really need to move to is a perspective that's more like marginalization. We'd like an image that marginalizes over all the uncertainties in the phase screen. And this is something I've been working with Lindy and Katie Bowman at MIT and stuff to think about how we can kind of take VLBI imaging to that next step and really move beyond this kind of single image mentality. So I hope I've convinced you that there are a lot of applications of statistical universality in astrophysics. It's not just about data analysis. It can help us understand the source. It can help us understand our instrument. And it can help lead us to new analysis techniques that aren't necessarily directly motivated by the problem itself. And I think that there are analogies here with pure mathematics, actually. And so there are these wonderful quotes by Bill Thurston in this paper he wrote called On Proof and Progress in Mathematics. He says, what people really want is usually not some collection of answers. What they want is understanding. We are not trying to meet some abstract production quota of definitions, theorems, and proofs. The measure of our success is whether we whether what we do enables people to understand and think more clearly and effectively about mathematics. So likewise, in astrostatistics, I don't think the goal is to build a bigger and bigger black box so that we can get more and more accurate answers. We want to understand what we're doing, we want to simplify problems, and we want to be able to think more effectively about astrophysics in general. Thanks.
Stochastic Optics example.
Yeah.
You know, you've got a method, but I think the example you're showing is not great, right?
Yeah.
Because that image that you've reconstructed doesn't look like the original.
Well,
it's better than what you had in between, than the two sources. It's better than two sources, but I think just in terms of presentation,
sure.
you start with a case where it really is very good, and then you can say for the real case, it's still not quite good enough.
Yeah, absolutely.
Would that be the correct statement?
Well, this is at 100 gigahertz. I've deliberately gone to a frequency. So here the scattering is much stronger than EHT. We wouldn't hope to be able to resolve fine scale stuff here. The comparisons are a little more subtle for 230 gigahertz.
You take the screen that you reconstruct.
Yeah.
And then did this at, let's say, really at 1 millimeter. With 1 millimeter data. Would you then get something that looks like the real thing?
Yeah, absolutely. So with 1 millimeter data, what happens is you do get spurious features, but they don't look quite so bad. So in this case, we get these two lobes or something horribly wrong. For 1.3 millimeter, you get an image that looks okay, but it's got, maybe small, compact, discrete features.
Yeah, and I'm asking the next step.
And then when you apply
100 gigahertz to help you to solve for the screen, and then you put it on the 1.3 millimeter data.
So actually what I've done is one step beyond that. You actually take the 3 millimeter and the 1 millimeter, you analyze them simultaneously with the same screen, and then it does wonderfully.
Why did you show us that?
Well, all in good time. Yeah, well, this is all sort of in prep, which is why the axes are horrible. But
Actually, the other obvious question is how many EHT stations or VLBI stations are assumed in the reconstruction?
So this reconstruction, well, bearing in mind that this is 100 gigahertz, but this assumed the 2017 EHT arrays. So it involves South Pole, ALMA, the SMA, SMT, with expected thermal noise at all those sites. Oh, and the LMT. Yeah, so this is an expected realistic observing array. It's not. I haven't taken this to some crazy regime for an array that won't exist for 20 years or something. This is really a technique that should be applicable to data we already have. No time variability in the source or in the scattering, both of which can potentially help you. But I mean, the most exciting thing to me about this is just that we've taken one data set and we've reproduced two images, both of which are informative. This is exciting because if the source is time variable, maybe we can reconstruct a static source plus a movement map of the source. Maybe we can, take other, we can reconstruct other things that are lurking in the data. We don't have to be in the single image mentality. Well, so my favorite example of this is in VLBI, you use the rotation of the Earth to improve your imaging. And, well, you know this, of course. The rotation of the Earth means that, you observe for timescales of hours, and that builds up this coverage that you have. You sample more spatial frequencies. If the source is evolving on shorter timescales, and if you can understand that evolution, then you can use that to do imaging far better than you could ever have done if the source were steady. So it's just a question of how regular the evolution is of the source. If it's really random, stochastic, yeah, then it's going to be a mess. But if it's some smooth movement and accretion flow or blobs being ejected from jets or something like that, you'll actually improve your imaging once that's understood.
So I'm just curious to know, what do we know about the scattering screen now that you have multiple observations at multiple frequencies? Does it stay very? What makes it?
So I would say we know very little. What we know very well is the angular broadening of the source, how much it's smeared out as a function of frequency. That depends all on very small scale features of the scattering, scales of hundreds or thousands of kilometers. What we need to understand to do this type of mitigation is to understand the scales more like an AU, or a fraction of an AU. Right, so the magnetar is an interesting point. It's sort of like a laser for adaptive optics. Maybe the magnetar is our point source that lets us understand the large-scale statistics. So this is something, in the next 5 years, we'll know it perfectly, but right now we know very little. Yeah.
Any last questions? With that, let's thank Michael again.
Thanks.
Very well timed, Nicole. Yeah, really good.